Hi, folks. Professor Brad Gibson here, head of the Department of Physics and Maths at the University of Hull. I hope you and your family are safe and well in these trying times. I wish we could be meeting up in person to walk through some of these things together, but I promise we'll make up for that later in the year when we're all back on campus safe and sound. Just wanted to take a few minutes to introduce some of the work that we do within the EA Milne Centre for Astrophysics, which is sort of the research wing of astrophysics embedded within the Department of Physics and Maths as a whole. The center has been in existence for about 5 years now. We've gone from 0 to 25 staff and students during that period of time, one of the fastest growing centers in England. Our research covers everything from solar physics to stellar physics, the origin of the chemical elements, the formation and evolution of galaxies, and large scale structure. And I don't have time to go through all of them today. And I'm going to pick out one or two interesting bits that we're working on right now, since that will impact on some of the research projects that you may be doing downstream, whether you're in astrophysics or physics. The key part of that word astrophysics is physics. So there are projects embedded within the work that we do that are related to data science, data mining, data imaging that you in the physics side of things may be interested in, whether or not you're thinking of astrophysics as a career or not. We have the benefit of working very closely with a number of people that some of you may recognize. People like Martin Rees, the Queen's astronomer, the Astronomer Royal for England, Dame Jocelyn Bell Burnell, the discoverer of pulsars, some of the most extreme objects in the universe. Helen Sharman, the country's first astronaut, born not too far from Hull in Yorkshire. Helen, in particular, has been here very recently, going into schools and colleges with me and doing public events around the region, most recently as part of the British Science Festival. And here Helen is with some of our students, and not one of our students, but my daughter Esme as well. And most recently, Michael Foale, one of the country's most decorated astronauts, one of the few to spend more than a year in space. The reason I put them up there is not to just sort of show off these people, it's that they have the same philosophy and ethos that we have within the physics department as a whole, and that relates to widening participation and trying to better engage with underrepresented groups. Now, over the last few years, they've worked closely with us and a number of our students, including some of the ones that you can see here, in trying to redress some of the imbalance that exists within the gender diversity in physics as a whole. Over the last 3 years, we've doubled the number of women into physics with this Changing Face of Physics campaign, which we were awarded a bronze award by the UK Quality Challenge Unit. And we're broadening that out much more than just gender diversity, looking at underrepresented groups as a whole in the physics community. With the support of our alumni, we'll be offering two £1,000 bursaries to qualified BAME students for entry in 2020. And another aspect of what we do within astrophysics, it's a very visual science. I'm not naive. The university didn't invest heavily in the growth of this Milne Centre simply because they had a love for astrophysics, but they saw astrophysics and astronomy and the space sciences as a way to reach out to the next generation of scientists that are needed for the economy going forward. And so outreach and engagement is a really big part of what we do. And I'm drawing it to your attention because there's plenty of opportunities as undergraduates from the day you walk in, whether it's foundation year or first year direct entry, to work with us in engaging with the community. We have a mobile planetarium. You can see in the bottom left there, that is run by our undergraduate students. They design the shows, they present the shows. We've reached maybe 3,000 students over the last 2 years, I think, around the region with the mobile planetarium. And all of our efforts combined, something like 3 million over the last 5 years, about 100,000 of those face-to-face and the rest through our online activities. And a lot of those are underpinned by people exactly like you, undergraduates who come into schools and colleges and scouts groups, guiding groups, University of the Third Age, various public events supporting the work that we're doing. So I put that up there because it's an opportunity for you if you want to get involved in outreach and engagement to help support what it is in the broader mission for physics as a whole. A lot of our expertise is based around high performance computing, supercomputing if you like, and I'm just going to show you a couple of highlights related to galaxy physics and the large data sets that require sort of advanced data mining tools. And it's a big part of the project offerings that we do, both during your formal projects in second, third, and fourth year, as well as summer research internships that you can take on. So if you're interested in modeling the universe or modeling individual galaxies like the Milky Way, which is a big part of my research, we need three components. You need initial conditions. You need to take those initial conditions and marry them with physics. And then occasionally you have to make use of boundary conditions so that your physics don't go wandering off into odd recesses. I'm not going to spend a whole lot of time on the initial conditions and the boundary conditions, but just focus a tiny little bit on the physics because it links in with work that you guys have been doing over the last year as part of your A level. So what is the physics that underpins the sort of simulation that you can see there right now? Where I like to begin with this may seem like a strange place, but it's going back to the 1840s, 180 odd years ago, into Ireland. This beautiful telescope, almost 2 meters in diameter, built by William Parsons, called the Leviathan of Parsonstown. It was the largest telescope in the world for about 70 years until the early part of the 20th century. This telescope was built, and as you can see from the skyline there, not in a particularly great site for observing, but it was built to address this question of the nebular hypothesis. And basically, it was just, when you take a telescope and you point at certain objects, they look a little bit fuzzy. And there was a debate at the time in the mid 1800s about what the nature of these fuzzy things were. If you built, half the people thought if you built a big enough telescope, you would be able to resolve these things into identifiable structure. And then some fraction said, doesn't matter how big a telescope you make, they're still going to look like fuzzy blobs. We now know both sides were right. Some fuzzy blobs do resolve into identifiable structures, some do not. But that's a whole other topic. So the first thing that Parsons pointed at was his beautiful galaxy called the Whirlpool Galaxy, M51. And this was the sketch he saw. He looked at the eyepiece, drew this thing, and proclaimed success that, if you build a big enough telescope that you can resolve it into stellar spiral structure. And so that was a great success at the time. And we kind of take this for granted now, 180 years later. We understand all of this, and so the significance of that, if you like, has been lost to the mists of time. But maybe the thing that hasn't been lost to the mists of time is that white little blob attached to the side of the Whirlpool Galaxy. That's really, in retrospect, probably the greater discovery, if you like. And that it's telling you that galaxies are not isolated islands, that they do not form and evolve by themselves, but in fact they interact with their environment. They evolve, they assemble, they accrete, they bring in satellite neighbors, tear them apart, and this is how galaxies grow and evolve through cannibalism, if you like. And that is still, 180 years later, a very hot topic in the world of astrophysics. What is the process of merger and assembly? How does it work in different environments? How efficient is it? When Parsons made this sketch in 1845, he may have had it in the back of his mind, like, what is this thing? What is the impact? You can see just by eye, by looking at his sketch and also the Hubble Space Telescope picture, that it's drawing out a spiral arm from M51, so it is having an effect. Now, the natural question would be, well, what is this thing going to look like in the future? Now, when you take a snapshot with the telescope, you're sort of stuck. You can't wind the clock forward or back. You can make educated guesses. The way we make those educated guesses now, if you like, is by using supercomputers to do this work. And what we would do is we would represent a galaxy with millions, possibly billions of particles, what we call n-body particles, where n can be stars or gas clouds or dark matter. It's just a way to represent the galaxy in terms of a number of particles. Now, great, we can do this now with apps on your smartphone. You can build up to billions of particles inside of supercomputers, which is the work that we do. Wasn't really an option for Parsons in 1845, but the underlying physics there had been known for a couple of hundred years, thanks to Isaac Newton, and it's no more complicated than what you've been doing over the last few years in A-level and possibly GCSE, and it is the inverse square law of gravity. Stars obey the inverse square law. The dark matter that binds together galaxies and the universe as a whole obeys this inverse square law. And gravity, sound, light, heat, magnetism, electricity, all of these things obey the inverse square law, which just means, as I think you all know, if you take two particles and move them a factor of 2 away from each other, the force of gravity between them doesn't drop by a factor of 2, it goes down by 2 squared. You move something 10 times further away, it doesn't go down by a factor of 10, it goes down by 10 squared, or a factor of 100. Simple as that, the inverse square law. And so what we can do now inside of a supercomputer is we can put millions and billions of particles and we can loop over all the particles and work out what that inverse square law is between all the adjacent particles, and discover and determine what the net gravitational effect is on an individual particle, and we can adjust its position and then loop around all the other particles, and we can slowly evolve this system forward in time. And so there may be millions, there may be billions of particles in our supercomputer, but at its heart, this is what is underpinning it. The physics is just the inverse square law of gravity. So I'm going to take a step back from the physics and just very quickly in one slide say something about the initial conditions. So what are the initial conditions? If you're interested in evolving uh, individual galaxies or larger scale structure in our universe, what we do is we go back to the beginning. We go back to the Big Bang. And the first thing that we can actually observe, it's about a few 100,000 years after the Big Bang. It's called the cosmic microwave background. That mottled pattern of blue and red and orange and yellow that you see there are subtle, subtle temperature differences as you scan across the sky. And those subtle, subtle temperature differences tell you very clearly what the underlying distribution of matter, both dark matter and the normal matter that we are made out of in the universe, as well as even more mysterious components of the universe called dark energy. But when we look at that mottled pattern, the CMB pattern, we can also look at how galaxy numbers evolve with time and how galaxies rotate. All of that put together tells us that about 15% of the matter in the universe is normal, the stuff that we're made out of, what we call baryons. The other 85% is dark matter. Now, we don't know what it is. It's the next Nobel Prize to come will be whoever can figure out exactly what dark matter is. Now, we can't see it, but we can certainly feel it because dark matter dominates the matter content of the universe, and it only interacts by gravity. It doesn't absorb light, doesn't give off light, but we can sense it, we can feel it, we can see its influence through the force of gravity. And because 85% of the universe is dark matter, it actually makes it really simple to model. Like I said, the gravity is simply the inverse square law. So the vast majority of the matter content of the universe doesn't require a whole lot more than the inverse square law. And so one of the things that you can do is you can take those initial conditions, that temperature distribution, which tells you what the matter distribution was a few 100,000 years after the Big Bang, and just throw all of those particles into a computer and turn on the inverse square law and let time run forward. And what you find is that with nothing more than that cosmic microwave background as your initial conditions and the inverse square law of gravity, you actually do a really good job. You get this rotating topological representation of what the universe looks like. And when you go through and measure these statistics of how much is in filaments, how much is in voids, and then compare with what you actually observe, which is what you see in the bottom left, actually, statistically, they're more or less indistinguishable. So very simple physics, plus the initial conditions of the cosmic microwave background, allows you to get a pretty darn good representation of what the universe looks like, which is quite remarkable. Now, where my interest comes in is moving away from that large-scale topology of the universe and zooming in on individual galaxies like our Milky Way. And so the models that succeed on large scales really didn't work so well on small scales. The first attempts to model things like a Milky Way galaxy using supercomputers at the time in the late 70s and early 80s with just the inverse square law failed. Here shows a few snapshots where they've taken two galaxies represented by n particles and thrown them at each other to try to recover something that looked like a spiral galaxy. And they didn't. They were able to recover things that look like elliptical galaxies, but we didn't get anything that looked like the Milky Way that we know and love. And so we now recognize that what the problem is there's some missing physics there. Gravity does cover sort of 85% of the matter in the universe. It's simple, it's elegant. We can put millions of billions of particles into our supercomputer, but it's only part of the story. That other 15% of the matter in the universe, the baryons that we're made out of, they do feel other forces beyond just gravity. And so to model that 15%, which is the galaxies and stars that we observe, we need to move beyond just the inverse square law and just gravity, and it requires more complicated baryon physics. It's what we call fluid dynamics or hydrodynamics. And even if you haven't done them formally in A levels, you conceptually understand probably the concept of fluid dynamics. If you take a glass of water and you pour it into a bucket, it sloshes around in a way that you can picture in your mind. If you take oil or treacle, do the same experiment and pour it into a bucket, it's not going to slosh around the same way because it's a lot more viscous, it's a lot more thick. even though both experiments are obeying the laws of fluid dynamics, the equations of hydrodynamics, it's clear that it's not simply just the inverse square law of gravity that is governing how those things slosh around. There is this extra wrinkle, if you like, viscosity. And so what we do inside of our simulations now is we represent that fluid as a whole bunch of particles that both feel gravity but also feel viscosity. It's exactly the same representation for gases and liquids that is used in all of these different industries: aerospace, automotive, and the renewable energy, wind farms, the design of turbine blades, structural engineering, doing natural disaster simulations, erosion simulations. They're all using exactly the same particle representation for fluids and gases that we use in our astrophysical simulations. And more than that, just taking a look at those different industrial applications that are shown right there, they're actually using software that was invented by astronomers 40 odd years ago. It's called smooth particle hydrodynamics, SPH. All of those engineering simulations we're generating use astrophysical software. It's just sort of this classic example of blue skies research that impacts in all avenues of science and engineering. And it comes back to one of the reasons why physics and astrophysics degrees are have such a high employment rate, amongst the highest of all the STEM degrees. Not because people necessarily become classical physicists or classical astrophysicists. It's because all of the tools that we use in our community are the same tools that are used in a huge number of other industries across the financial sector, in terms of financial forecasting, economic forecasting, the data science community, all those industrial applications I just showed you. So, when we design our projects for you to work on, we're thinking very carefully about your career prospects. And yes, 1 in 10 of you may decide you're going to become a classical physicist or astrophysicist like myself, but 90% of you are going to take those skills and move off into different sectors. And so we're very careful in the design of our projects not to just be doing blue skies research for the sake of doing blue skies research. Yes, we're trying to answer these big fundamental questions about galaxies and how they form, they evolve, but we're also thinking the whole time in the design of your projects about what it is that's going to make you employable at the end of the day. Now, so coming back to where I was, what happens when you take the inverse square law and now combine it with the fluid laws? What did we hope to get? Well, this is the sort of thing, if you're interested in Milky Way, galactic archaeology, which is sort of the work that I do, combining inverse square law, fluid dynamics, we'd hope to get big but thin disks. These are sort of a wide range of disks looked at face on, edge on. They're big, they're extended, there's small bulges of light in the center, nice spiral arms. Unfortunately, the first experiments that were done, and this field is it's less than 30 years old now, 25, 30 years old. The first attempts to combine inverse square law with fluid laws, this is what they actually got. They're blobby things that kind of, if you look at them sideways, they do kind of look disc-like. But they're nothing like the pictures of the grand design spirals that I just showed you. They're stubby, thick discs, big spheroidal bulges, no obvious spiral arms. And over 15 years subsequent to that, through the early aughties into the late aughties, all that advancements in hardware and software technology had improved things, as you can see here from the 2003 2007 state of the art. But there's still this fundamental mismatch between things that look like real grand design spirals like the Milky Way. And where we came in is we recognized that there was this, what we would call sort of an energy crisis. And we needed to find a way to stop all of the gas flowing into the center of the galaxies, becoming super dense, starting nuclear fusion, and most of the stars forming in that inner dense part. And it was just too efficient. The gas just would, because gas feels viscosity, it rubs, it loses energy, and it falls into the center very efficiently. We needed some way to heat up that energy and push the gas away. And the source of that energy largely comes from exploding stars, supernova, sort of the fate of stars that are 10, 20, 30 times heavier than the sun. Each supernova, when it explodes at the end of its lifetime, that may be 10, 20, 50 million years after its birth, the same amount of energy as sort of a billion of the most powerful nuclear weapons on Earth. So there's an incredible amount of energy associated with these. One explodes every 10 years in our own Milky Way. And it's that energy that we tap into to stop the gas from flowing and piling up in the inner part and forming dense, stubby disks. And so we've got to a point now, and this is only in the last sort of 5, 7 years or so, of getting things that, on the top you can see observed spirals, and below you can see some of our simulated spiral galaxies. And it's getting to the point now where you can't tell the difference anymore between a simulated galaxy and a real one. And this is all making use of this advanced feedback scheme from exploding stars to get the balance right between gas flows in and out. Um, where we stand today, right now, the next generation is a massive project that we started with the Korea Institute for Advanced Study. It's called Horizon Run 5. This is really pushing the boundaries of what you can do in computational physics as a whole. We're moving beyond gigabytes and terabytes and petabytes into the exabyte scales. These are massive, massive data sets that we're generating. In the bottom right is one of our simulations of a spiral galaxy as it's evolving. That's our expertise, marrying inverse square law and fluid dynamics to do these high resolution simulations of individual galaxies. On the left is the expertise from our Korean collaborators in Seoul, who really are experts in large scale structure, particularly with using just gravity, dark matter simulations. And so our high resolution simulations on the right would fit into 1/100th of a pixel of what you see there on the left. So what we have done is we found some very clever ways to take our hydrodynamical approach and marry it with those enormously large-scale inverse square law approaches. The Horizon Run brings the best of both worlds together. It's about 100 times larger than anything that's been attempted before. Just to show you graphically, here's Illustris and Eagle. These are the two biggest computational simulations that have ever been undertaken in the field. Illustris is from the North American groups, Eagle from the European groups. What our approach with Horizon Run is a long cylinder, about 10 times larger than any of the individual boxes that have been done before, spanning a huge long range in scales. It allows us to probe the largest scales in the universe that could never have been done before, but at the same time also getting thousands, tens of thousands, hundreds of thousands, potentially millions of individual galaxies that we can also look at the gas and the stellar properties. It has just finished running, in fact, just about 2 weeks ago, so 350 million core hours, split between primarily with the Korean supercomputer facility and using the University of Hull's Viper facility, which is one of the most powerful in the country, certainly one of the most powerful owned by a single university, and something that all of our students have access to when they start up. Myself and my colleague in Seoul, Changbom Park, are the PIs, and we have an amazing amount of work that has been done by staff within the Milne Centre in the physics department here. Gareth Few on the left, whose code underpins Horizon Run, and Leah Cox is working on her PhD with Gareth and I right now. So I'll go on to summarize everything you've seen in a science sense. I guess these are my take-home messages. Don't be afraid of astrophysical simulations. Very often they're not much more than very clever algorithms to mimic the inverse square law, and in some cases, fluid dynamics or viscosity. Simulations such as the ones I showed you do really well on large scales with just nothing more than the initial conditions of the cosmic microwave background and the inverse square law. When you get down to smaller scales of individual galaxies, you need something more. You need fluid dynamics, baryonic physics, and that's where our team comes into play here at the University of Hull. And at the end of the day, we are thinking very carefully about employability. So yes, my interest is more in the broad science questions, but I never lose sight of the fact that at the end of the day, I want to make sure that you walk away employable. If you want to follow up with me offline, I can talk to you about some of the examples of our students and where they've taken those software skills to go off and do amazing things outside of the astrophysics community. So last thing, just to summarize, why would you come to Hull? Why would you be interested in astrophysics at Hull, physics at Hull? Some of this you may have heard before, but I just want to drive the point home. We do have excellent employability and salary prospects looking at our graduates, amongst the best in the country. We have probably the country's leading work placement internship scheme supported by the UK's Office for Students. We are the lead institute for RIPA Plus, which is the White Rose Industrial Physics Academy. And we do have a number of summer research placements that are supported by our alumni who've donated generously to support our aspirations in physics and astrophysics. I think the support, the individual attention, for me is unique in the country. I've been in the UK for 15 years, higher education for 20, 25 years now. This is the friendliest, nicest place I've ever worked. You are a name, you are not a number. We legitimately have an open door policy for all, very accessible. That's not going to change whether we're on campus in the autumn or in the winter. You can contact me anytime, 24/7, uh, and all of the staff have exactly the same philosophy. You're a partner with us, you're involved in and invited to seminars, you'll meet world leaders on a weekly basis. I've alluded to this previously, but your undergrad projects are not canned experiments, they're unanswered questions in science. You are a colleague, a peer, a collaborator. Our goal is to try to get the work that you're doing published as papers, so we have a vested interest in working with you as a collaborator, as a peer, rather than as a traditional instructor slash student. You have access to Viper, one of the country's most powerful supercomputers. Our expertise is along the lines of the origin of the chemical elements, intense solar storms, largest structures in the universe, galactic archaeology. Everywhere you go for open days, applicant days, offer holder days, you'll see a different list of expertise, but those are the areas that we are the world leaders in. And at the end of the day, we are, in my experience, the most sociable, supportive, fun group in the country. And for the parents in the room, that can also be important because you will be spending 3 to 4 years of your life with us, and more likely than not, I will be seeing more of you than your parents will. So it's important for both parties to be comfortable in the decision. So thanks for taking the time to listen to this. I am accessible, like I said, 24/7. Drop me an email if you want to have a Zoom, a Skype, a FaceTime, whatever the case may be. I'm more than happy to chat one-on-one with you whenever you need to. You can follow me on Twitter. If you have some interest in looking into a little bit more of the work that we do, I have a TED Talk out there on YouTube on the search for alien life, and a number of other things out there on YouTube that you might want to track down. But again, just drop me a line if you want to chat some more, if you have any other questions. And thanks again for taking the time to listen. I appreciate it. Take care, folks.